Welcome back, everybody. So before we start, so this is a new part on relational algebra. I just wanted to show you this. So I tried what was asked earlier by one of you. So here, I'm creating a table with two columns, C1 and C2, right? Then I'm inserting values in there, 1, 2, 2, 3, 4, 5. And then I'm, you see this select star from, this is it, right? It's a select star. And then you see the nicely displayed table with column C1, column C2, and these are all small ints, right? So integers. Now, if I try to create another table with a column C3 that is also a small int, and I try to reference C1, so the column right here, is going to fail. You see, there is no unique constraint matching the keys for table 1. So it refuses to create a foreign key on that, even though it is unique, right? But I did not enforce it as unique. So how do I enforce it as unique? Well, there is this command here, alter table, blah, 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 add unique C1. It's going to succeed because the values are unique. And then if I try again, then I can now create my foreign key. So you see how it went. The data was unique, but it wasn't enforced. So I have to first add the constraint that it must be unique, and then I can create my foreign key, right? Does it make sense? So I really encourage you. So this is the Docker. I just took the Docker that you have in there. You can put whatever you want in there and create queries. I really encourage you to do it. There is nothing better than doing it to actually understand how that works. You can experiment, you can try things out, you know, and play with it. We will also give you data sets at some point that you can query. So yeah, that's the nice thing about this course. It's really that it's very practical, and you can just write all that SQL yourself. But now we are going to have a small parenthesis, right? So I'm going to teach you some math, so some more formal aspects of the relational algebra. And then next week and the week after that, I'm going to show you how you do it in SQL, all of this. So that's a reminder, things we've already covered, but it doesn't hurt to repeat it many, many, many times. What is a relational table? Well, it's a set of maps where every map is a row, a record, and it also additionally fulfills relational integrity, domain integrity, and atomic integrity, right? And we've already seen that relational integrity, it's kind of okay if it's a bit broken, right? But only if it means that some values are missing, right? But basically, normally you enforce these three, okay? And this is where we are. Now we know how the tables are formally defined. We know how to do it in SQL, how to define the structures of the tables. Now we want to manipulate them. So we already know how to insert data and how to delete data and how to update data. But what I want to make now is to make it flow around. I want to query data and actually extract information from tables. So today is going to be data manipulation and not data definition anymore. So relational model is the name of what we've covered so far with the definition as a set of maps or bag of maps or list of maps. And now enters the relational algebra. So you've all been to primary school, right? So in primary school, you're taught addition, multiplication, division, and so on. You work it on integers, then you do it with decimal numbers or fractions. And then you noticed a few things while doing that. For example, you noticed that 2 times 3 gives you the same thing as 3 times 2, right? You can swap the sides, still the same thing. You might also notice that if I say 2 times 3 times 4, you can either start with 2 times 3, 6, and then times 4, or you can start with 3 times 4, 12, and then 2 times that, right? In fact, there is a mathematical genius that lived in the 19th century who's called Évariste Galois. Anybody heard that name? Never heard that name. So he was probably even younger than many of you. He was 18, 19. And he basically noticed these patterns with its primary school math, right, that we're looking at. But he basically noticed that this idea that you swap the sides and it doesn't change the results, or you start computing from the left or from the right and so on. It has a name. It's called commutative associative. So this is how it's called. But what Évariste Galois did is he abstracted away from that. He said, let's just generalize this notion of plus, times, or addition, multiplication to something formal, right? So I have a set that contains values, could be integers, but actually could be anything. And then I have a binary operator like plus or times, but it could actually be anything. You could just make up a symbol for that. And then you can start assuming things. So you can assume that this binary operator commutes. You can swap the size. You can assume it's associative, meaning that you can compute in any order you want when you have 10 values to combine. You could also introduce the notion of what's called a neutral element, right? A neutral element means that when you use that operator with the neutral element, it doesn't modify the value. For example, 0 is the neutral element for addition. Plus 0 doesn't modify anything. 1 is the neutral element for multiplication. 1 times something doesn't modify anything. You also have the notion of inverse, right? So for example, if you say 2 plus minus 2, that gives you 0, right? So that's called an inverse in the language. Technically, it's called opposed for addition, but opposite. But for example, for multiplication, then the inverse of 2 would be 1/2, because 2 times 1/2 gives you 1, and the neutral element. And basically, Évariste Galois abstracted this away, giving some definitions. So for example, if you have an operator like that, that is associative, that has a neutral element, and where everybody has an inverse, then basically you can call it a group, right? And so the notion of group, then the notion of ring, the notion of field, you know, all of that basically was born from this. At the time, nobody took him seriously. Like the reactions back then were really like, this is just a toy, you know, you're playing in your sandbox, but this is not very serious. Very sadly, he died very early at a young age, and that was only recognized later. But now he's considered to be the originator of all of these groups, fields, and so on. And now it's everywhere. In physics, in computer science, like these algebraic structures are absolutely everywhere. So it started with numbers, and then we realized that you can also do it with matrices. Who's ever seen matrices? Right? It's very commonly used in linear algebra and so on. And you can multiply matrices. You can add matrices, right? So this is a whole generalization. In fact, matrices are even so powerful that any group, finite group under some conditions, can be represented with matrices. That's called representation theory. But so these are examples of matrices. So the reason I'm telling you all of that is that it gives you a framework when you have sets of values and you can manipulate them and combine them and do calculations with them. The really cool thing is that you can do the same with tables. That's exactly what we are going to do today. We are going to take tables and we are going to build some operators on them, unary operators, binary operators, and create new tables out of other tables. This is really like the mathematics of relational tables, right? So I wanted to give you that background for it. So this is here a binary operator because it takes two tables and creates one table out of it. This is a unary operator because it takes one table, creates one table, right? So it depends on the number of inputs, binary. So what are we going to have in this mathematics of tables? We'll have set queries, set operators. So union, intersection, subtraction. Of course, I'll go into details of all of that. We'll have filter queries. We'll be able to select from a table. We'll be able to project a table. We will have renaming queries where we can create new tables that have different column names or different table names. We'll have shuffling queries that can actually do some aggregation or some sorting. If you have lists of maps, of course, you need an order for that. So if it's the list of maps, you can sort and create a new table with a different order. I call them shuffling query. The term shuffling actually will be clear if you go to big data for engineers. And we have joining queries that take multiple tables. For example, a table with primary keys and another table with foreign keys referencing the first one. you can join them. That's called the join. So this is called joining query. So we look at the Cartesian product of two tables, the natural join, the theta join, and so on. So you see, it's enormous. There's so many things you can do with tables. And in fact, tables are just like numbers. These are just mathematical objects. And we can just define these operators on them, right? So that's a bit as an appetizer. All right. So this is a relational table. So I try to always use that convention that I have the column names in there, and then I have the in yellow I have the domains, the types, because we have domain integrity, and then I have the values, so the actual records. So here there would be 4 records. Now, something that I kind of did already in SQL is I gave names to the relations, right? So I added then this black row here are, well, the fancy name for that is a rel var. It means relational variable. That really means just it's a mathematical variable that is the name of that is assigned to a relational table. So that's the name. But there is a thing that some mathematicians wouldn't really like this very much, but it's the fact that when you have a variable, for example, x, and you assign x to 2, say x equals 2, let x be 2, 2 doesn't know that it's called x, right? But in the case of a relational variable, the relational knows its name. So you also, the idea is that the way you name it is actually also considered to be part of the table. So this is why I add it over here. So it's not just a mathematical variable, it's also extra information that is part of the mathematical object. All right, but really all I said here is we give a name to the table. That's really all I said, right? We call it R, for example. Okay, I need that because that's part of the math when we rename the tables and when we use the name of the table to do some things. Okay. So I'll start. So this was my menu here, these 5 categories. So I just go down that menu category by category. Of course, I will not do everything today. I will just start. So let's start with the set queries, the first category. These queries are basically involving binary operators. We need 2 tables, and we are going to create a third one. Now I need some mathematical prerequisite, just to give you some formalism. So here I have again Évariste Galois in mind. So I have a set that I'm calling A. Here it has 4 elements in there that belong to A. Imagine that I have what would be a unary operator. A unary operator that I call tilde. It means that whenever I have a member, let's call it X, I can create tilde X, right? If it's Y, then it's tilde Y and so on. So it means that every one of these elements, if I use tilde, it basically brings it somewhere else. That's the result of tilde X that would be here. So this is X, this is tilde X. Now the question that you can ask yourself when you do that is, if X is in that set A, is tilde X also in the set A, right? Here it's the case. Tilde X is also in that same set. We say that it's closed. That's the set is closed under tilde, right? You basically remain in it. Here, if tilde X, so that would be tilde tilde X here. If you again apply tilde and you're outside of A, then it's not closed. Now, here's an example of that. If I take the set of integers, positive integers, right? 1, 2, 3, and so on. And if I use minus, so the tilde would be minus. Do you agree that if I take 2 and I apply minus, that would be minus 2? Minus 2 is not a positive integer. So here we don't have closure. It's not closed under minus. But if I take the set of all integers, positive or negative, then it is closed under minus. Who agrees? Okay. So basically, or we can also say A has closure under tilde. That basically means that whenever you apply tilde, you stay within that set. You keep staying there. Okay. You can also do it for binary operators. An example is subtraction. An integer minus another integer. 4 minus 3, that's 1. That's also an integer, right? 3 minus 4, that's minus 1. So if you consider only positive integers, then 3 minus 4 is negative, it leaves the set of positive integers. So you don't have closure. But if you consider all integers positive and negative and 0, then it is closed. So you can also do it with binary operators. You can ask if I have x and y inside that set, is x plus y also in that set? Right. Okay. Why did I tell you that? Well, I told you that because of what we are going to do now. Let me take two tables. They are shown here. One table has two columns, A and B. The other table has three columns, C, D, E. Mathematically, these are sets of maps, right? So I have a set of map on the left, and I have a set of map on the right. Each set of map has relational integrity, right? All the maps in the first table on the left have the same support AB, and all the maps, the four maps on the right, have the same support CDE. Who agrees? Right? Just formally. Now, can we compute the union? Normally, we can, right? These are sets. If I take two sets, I can do the union of two sets. It's just a bigger set that has the elements of both, right? So that's the union. So I could do it, right? So let me put data in there, right? So this is 6 records on the left and 4 records on the right. So I can do the union of that, right? If I take this and I just build a bigger set that now has 10, right? That's the union of the two. But do you see the problem here? Do we have relational integrity? We don't, because these 10 maps, they don't all have the same support. 6 of them have AB and 4 of them have CDE. So it means that we don't have closure. If I consider that I have a relational table having relational integrity, I take two tables that both have individually relational integrity, take the union of that, the union of the sets of maps. It's not a relational table because it doesn't have relational integrity. So the set of relational tables is not closed under union, because you could union two tables and get something that's not a table, right? Because of this is not a table. So the supports are not identical. So if you want to do the union in a way that you still get, that it still spits out a relational table, you need a few constraints. The first constraint is that the attributes should be the same, right? If I have the same attributes ABC on the left and ABC on the right, then I can basically take the union of that. And then I will have relational integrity. But do you see here that even though I might have relational integrity, I will not have domain integrity? Do you see why? I will not have domain integrity? Who can tell me? Yes? Exactly. It's a string on the left, an integer on the right, column A. So it means if you take the union, in the same column, you're going to have strings and you're going to have integers. So it's not the same domain. It's not in the same domain. So you would not have domain integrity. So you need an additional constraint. You also need for the domains to be the same. If they are the same, then we'll have domain integrity. And atomic integrity, we just need the domains to be atomic. And here they are atomic, so this is fine, right? So it means that we need these two constraints. The attributes must be the same and the domains must be the same. In practice, you will also want to order them in the same way when you use PostgreSQL, but this is just a parenthesis because since it's a map, there is no order in the columns anyway, right? But when I draw them on my screen, I will try to always put them in the same order to avoid confusion. Okay, but the practical with PostgreSQL, that we'll discuss next week and the week after that. Here are two tables. Do they have the same attributes? Yes. Do they have the same domain? Yes, so I can take the union and get a table with how many records, how many maps? 7, right? 4 plus 3. I have 4 on the top, 3 below. So that's the same attributes, the same domains, and I take all of the tuples in there. Okay. All right, so now I put a bit of math in here, no intention to scare you, but basically we have R that is this, S that is this, and we use this little symbol union to basically say that T is the union of R and S. That's part of the relational algebra. We can take the union of two relational tables if they have the same attributes and domains. Okay. Okay. Now, this is a case where there was no collisions. We did not have the same record in both tables. if we do have a record that is in both tables, we need to be a little bit careful. Because here it's foo 3 false, foo 3 true, so this is fine. But imagine that I'm changing a value here, I'm changing true to false in S, right? So now, do you see that foo 3 false appears on both sides? It means that the resulting output will have only 6 maps because one of them appeared twice. Why is that? Because I have sets of maps. In a set, you don't have duplicates. So this is the reason why, even though I have 4 and 3 on the 4 records and 3 records, I only have 6 because when you do the union of 2 sets, you will eliminate duplicates. For whom is that clear? All right, awesome. So now that we have the union, we can also do the intersection. It's the same symbol, but inverted, right? Like this. The intersection of 2 sets is the members that are common to the 2 sets that appear on both sides. What do we have here in common? How many? Two of them. Yeah. So we have the name, we have the same attribute, it's okay, the same domain, it's okay. And I have foo1 through, you see it's appearing both in R and S, right? Foo1 through, and foo 3 false also appears in both. This is called the intersection of the 2 tables. You need that same constraint that they must have the same attributes and the same domains. Okay, so that's the intersection. We don't need to worry about duplicates here because that's anyway tuples that are on both sides. But anyway, mathematically, you will not have any duplicates. And then you have, so this one is a bit more complicated. It's the subtraction of R minus S. So what we do is that we take all of the records in R that are not in S. So basically the ones marked in red here, foo1 through and foo 3 false, they are in S, so they would be taken out, right? So we only have the other 2, bar 2 false and foo bar 4 true, right? Who is following? Okay. Now, the notation for subtraction can vary. I just use the minus, but it's also common for sets to have the minus a bit like diagonal like this, right? You will also see backslash basically for subtraction, set subtraction. Okay, these are the 3 set queries: union, intersection, subtraction of 2 tables. Okay. And when you do the math on a piece of paper, you don't need to worry about the duplicates. If you just go through the records of R, you won't need to worry, right? Okay. Bit of warning, union and intersection is commutative. If you do the union or the intersection, it doesn't matter in which order the 2 relations are. Who agrees? Right? But it's not the same for the subtraction. The subtraction is not commutative. If you do R minus S, you will get what's on top. If you do S minus R, you will not get the same thing. Just like 3 minus 4 is not the same as 4 minus 3. Yes?
Subtraction is A minus B, but don't we have a difference argument? Like we will have a bar, foo bar, and foo bar in the last one.
I don't understand. Sorry.
Subtraction.
Yep.
Don't we have a difference method? Like the difference method would be the union of T and U.
So if you do, so basically, if you see a Venn diagram, so I have a Venn diagram in mind, right? You have R and S. You know what a Venn diagram is? It's 2 circles that are crossing. There are some memes on the internet with Venn diagrams. So basically, you have R and S crossing, and R minus S would be the partial part of the left circle without the intersection. S minus R would be the right side. If you take the union of the 2, you basically get the same as the union, but without the intersection. Right? Is it what you mean, or yeah? Yeah, yeah. Mm-hmm.
That appears only in one.
So they will be distinct. They will never overlap. Yeah. Yeah. See, I was almost tempted to do it on the blackboard, but if I do it on the blackboard, people on Zoom cannot see it. So, but just imagine 2 circles that are crossing. The intersection is the area common to the 2 circles. The union is what's in any of the 2 circles. And the subtraction, R minus S, would be the first half of the circle on the left. S minus R would be the second part of the circle on the right. Right. I'm not sure if I addressed your question. Yeah, but if there's anything else, we can also talk offline. All right. But the warning I want to give you here is be careful. You cannot swap the sides. It's not the same thing to do R minus S or to do S minus R, right? That's my word of warning. Okay. Okay, so we are done. If I go to my menu here, we had this, it's like the starters, the main dish, and so on. So many slides. So many slides. Yes, here. So we are done with set queries. And so now I'm going to the filter queries. Okay, filter queries. So the filter queries only need one table. I need one input table. So the first thing to say here is that I don't have any constraint. I can take any relational table and I can do some filtering in here. So the first kind of filtering is called a projection. A projection specifies a list of attributes that normally should be in the original table. So for example, I have a table with attributes A, B, and C. And I want to project on A and C. So what I get is a new relational table that has less columns. I have A and C, but basically I remove B, right? So I have just the specified A and C, and then I have the same domains as A and C, so these I don't change. And then I have my values in here. That's called a projection. For whom is it clear? Right? You can do it in Excel by hiding columns. You click on a column, you say hide, goes away, you basically get this, right? The only thing is that in Excel, it will not eliminate the duplicates when you do it. But when you project, it will eliminate duplicates if there are duplicates, of course, when you project. Now, we have a formula for that. And in the relational algebra, we love Greek letters. So we are going to use pi. Pi is projection. And then as a subscript of pi, we specify a list of columns that we project to A and C, right? So pi AC of R is this. Normally, and here I'm talking about the math, when you do it, these columns are supposed to exist in here. If they don't exist, imagine that I say ACD and ED doesn't exist, you could still consider that mathematically it makes sense and give it some definition, but it's not very useful, right? Except maybe when you prove some theorems that gives you corner cases. But again, typically, the columns you put in here should ideally be columns that are part of the relation from which you're projecting. Okay? So that's projection. So it really amounts to just picking a few columns and dropping the other columns, right? That's a projection. Now, a word about the duplicates. How can it be that duplicates can happen and you need to be careful? It's because we are removing column B, but look at these two tuples here. Foo, 1 true, and foo, 3 true. These two tuples only differ in B, right? A and C is the same, but they differ in the value of B. But if you remove the value of B because it's not part of the projection, do you agree that that would be a duplicate then? So you have to be careful when you compute that on paper that this has to go away. You cannot have any duplicates because this is a set of maps always. It's a set. So you need to always be aware that when you project, the number of records might be less than the original number of records because of that. So do not be surprised if you had 4 records here, you remove a column and suddenly you have only 3. That's because you have to pay attention to potential duplicates. Okay, that's projection on the columns. We can do the same things, but on the rows. That's called a selection. A selection requires what's called a criterion. It's a wish, basically. You want to select the records that match some constraints. Imagine that you say, I want to select all of the records that have B smaller than or equal to 2. Do you agree that the first 2 records satisfy this formula and the last 2 records do not, right? So what the selection is going to do is going to build a new table, but only with the records that pass the filter, that match this formula. So it means that I can build any expression I want. So here it's b smaller than or equal to 2, but I can do more things. I can do plus, minus, times, divided by. I can do smaller than, greater than, equal, different. So all of that. I can also use parentheses, and I can also use a combination with and, or. Do not be careful, just so if you never saw that. So that you saw in primary school, right? Plus, minus, and so on. That you also saw in primary school. Parentheses you also saw in primary school, but this might surprise you. That we don't see in primary school. This is logic. This means and. This here means and this means or, and this means not. Why is it useful? Because you could want to say b is equal to 2 and a is greater than 3. Or you want to say c is greater than 4 and d is not smaller than 2, right? If you want to have combinations like that, it's called a conjunction or a disjunction. If you want multiple criteria with and or not, with logic, this is the sort of symbols that mathematicians would use. This is for and, this is for not, this is for or, sorry, and this is for not. But don't worry, because in SQL, we don't use these symbols. In SQL, we have and, or, and not as English, so it's much easier to write. Okay, consider this a restaurant menu. This is everything that is on the menu, and you can use this in order to build any filter you'd like here. And when you're done, you just put it under yet another Greek letter. It's sigma, sigma for selection. And you put here whatever formula you want that is going to be either true or false for every one of these records. So if I take this one, it's matching here, it passes here, it passes here. It doesn't pass here, it doesn't pass here, because these two don't satisfy this. So I get a new relation with the new name. I get the same columns, I get the same types, but I have less records, just these two. For whom is that clear? That's called the selection. So now we have a projection and we have a selection. What's really cool is that it's just like addition, multiplication, and so on. You can combine them. So now you could take plenty of relations and you could say, for example, that some relation is relation R, union relation B, and then you put that inside pi for a projection AC, and you put that into a sigma, blah, blah, blah. So you can use pi sigma union intersection subtraction. So you see, you can already do some math here. You can already manipulate a lot of tables by combining all of these operators. Okay? When you do it on paper, you don't need to worry about duplicates, because if you just go through the records, so that's the algorithm now to compute the selection. If you go one by one through the records on the left, and you just eliminate those that don't match, you will not create any duplicates anyway. So this you don't need to worry about. Okay, so selection is like on the rows. You can also do it in Excel. The way you do it in Excel, just to have a visual analogy, is you select your table in one of the sheets, you select the table. I think you need to go to the menu data, filter data or something, or there's a ribbon data, filter data. What's going to happen is that you're going to see these small icons that appear in every one of the headers of the columns. And then you can click on them. And then there's a window that pops up and you can select the values you accept, or you can put some criteria and so on. And then Excel will automatically select the records you want. This is exactly what we do here. Here it's with relational algebra. In Excel, you do it with the filter data feature and so on. And we'll see how we do it in SQL next week. Okay? But basically, all I'm showing to you is the sort of stuff you can do in a spreadsheet software as well. I will explain, of course, why it's not a good idea to do it with spreadsheet software if you have a lot of data. I think that during COVID, it happened. I think it was in the UK. They did things with Excel instead of a relational database, and they had a mistake. Basically, they copy pasted some column somewhere else, and then it shifted the columns compared to each other, and then the data was basically wrong in the end, and that was all over the news because of that. If they had used the relational database, that wouldn't have happened. So this is, again, one of the benefits of having a relational database that would prevent you from shifting data or doing that sort of things. Okay? Still have a bit of time. I would like to say one more thing regarding pi. projection. So if you just use pi in the way I showed you here, it's just a list of columns, right? You just specify the columns and that fits. But in fact, pi can do a bit more than that. It can also do a bit of computation. You can also create new columns, compute it from the other columns. For example, you could say, I create a column D, and I populate it with the same values as in B, but +1. So all I need to say is B +1 a row D. So this is one of the ways to mathematically assign it. So I create a column D out of B +1. So now I get this. B is gone, right? I have A, C, and D in my output. So I have the same domains for A and C. D is kind of, you need to think about it, right? B was an integer +1 is also an integer, right? So D, we also take integer here, right? So now I have 2, 3, 4, 5 instead of 1, 2, 3, 4. That is called an extended projection. An extended projection also allows you to make up new columns and to compute them from previous columns. And again, to do the computation, you have plus, minus, multiplication, full bunch of functions. I think in SQL, you even have square root, cosine, sine, so all kinds of fancy functions that you can use in the formulas, right? For whom is that clear? That's an extended projection. Okay, I think I still have time for renaming because this is pretty simple. So it's not going to scare you before you go in your weekend. That's yet another Greek letter. It's rho this time. Rho like R, renaming. So what's happening here? Rho subscript A row D basically means that I want to rename column A as D. So it's exactly the same table, except that now A is called D. That's it. It's pretty easy. Really, the only thing that changes is the name of the column. Okay? And if you want to do that, it's row subscript A row D that creates a new relation with the different column name. Okay? If you want to rename the relation, well, this is where I'm not quite happy with the beauty of the math, because I told you earlier, it's the fact that the relation knows what its name is, and here mathematically it achieves a little bit, but nevertheless, if you just say S equals R, basically you created a new variable, a new rel var, that has the same content, but it just is named differently. It's named S. For the purists mathematicians who really want to do it cleanly and who consider that this information is part of the mathematical object, you would use row S that basically explicitly says that you create a different relation that has the new name S, right? So this is if you just wave your hands, and this is if you really want to do it cleanly with row S that says we do rename it to S, and that's something different. Okay, for whom does that make sense? So pi, sigma, rho, union, intersection, subtraction. Now you have 6 building blocks. Do you see that it's starting to look like a Lego game, right? Just like in primary school, you have addition, multiplication, like here we have rho, sigma, pi, and sounding like these organizations in the US, rho, sigma, pi, and union, intersection, subtraction. Okay? Should I scare you with more things, or should we take a weekend? Who wants to see a bit more? Who wants to go for the weekend? It's kind of tight, so let me show you more. We have something that's called the Cartesian product that we already saw. It's this multiply sign, the same multiply sign as for multiplication. So that I get out of two relations. So I have R and I have S, and I'm computing the Cartesian product between R and S. What I'm going to have basically, it's literally the Cartesian product of the sets of maps. It means that I need to combine every one of these maps with every one of these maps. How many combinations do I have? 6, 2 times 3. Every one of these 2 can be with every one of these 3. So I'm basically going to get a new relation where I have ABC and DE, and I'm going to have the domains that come from here. And I have all of the possible combinations. So these 3 combinations take from this one, these 3 take from that one, but I combine them in all possible ways. And here, this is where I have to mention, because that was discussed I can't remember if it was just in an email or on the forum. I think it was just in an email, so I can tell you. So somebody observed, and they're absolutely correct about this, that the Cartesian product is not associative. If you're really a mathematical purist, then A Cartesian product B Cartesian product C is not the same as A Cartesian product B Cartesian product C. Depends on the order. But in fact, for relational databases, we don't really care about that because we flatten everything. So technically, if I am let me put my mathematician hat, and I consider the Cartesian product between these two, what a mathematician would tell you, they would say, be very careful. What we actually get here are pairs. We get a pair that is made of this map and of this map. So a mathematician would tell you we get pairs of maps. The database researcher will tell you, no, you're overdoing that. What you really get is one map with 5 mappings. That's it. That's what you get. So you need your database hat and not your mathematician hat for that, right? So really what's happening is we flatten everything, and we really get, when we combine that map with that map, we get yet another map with 5 different values. For whom is that clear? All right. There is one little constraint that I have here. This is why I'll come back to next week. Do you realize that this works if the names are not overlapping? I need columns here that are completely different from the columns there. Do you realize that if I have the same column name here and here, then I'm going to have a problem when I do that, because then I'm going to have 2 columns with the same name. So here you need to be a bit careful when you do that, because that wouldn't work. So in other words, if you try the Cartesian product, for a database person, that doesn't make any sense to do it if there are columns with the same names. So what happens is we use row. Row comes to the rescue. So if I have a relational table and there's an overlapping column, P and B, it's not a problem. Let's change the name on one of the 2 sides. So I basically take S, row E renamed to E. So now I got rid of the problem because now it's no longer called B, but E. And now I can do the Cartesian product, right? So just keep in mind, if there's a column in common, we need to rename first. For whom does that make sense? Okay, you're doing great. So now let me just check how much you followed, and then I'll give you your freedom. Probably need to refresh. That is absolutely perfect. So everybody above 80%, and some people even understood everything. Somebody below 80%, it's okay. I mean, this is part of the learning. So you can maybe re-listen to the recording. You can read, you should read the textbook. By the way, I'm putting on the Moodle chapters of the textbook. You should read them. You should do the exercises. And you're free to ask any questions you have. You can ask them on the Moodle forum. You can send us emails to the TAs or to me. But of course, on the Moodle forum, it's best because everybody can see the answers. All right, but this is great. So you're doing well, and the pace is good too. So thank you very much. Enjoy the exercise sessions tonight or on Monday. Enjoy your weekend, and I will see you next week for the continuation of the relational algebra. Thank you very much. Have a good weekend. Thank you, Cheng.